Today we are going to discuss about losses in magnetic materials. Losses in magnetic materials. Magnetic materials in the sense iron core. When you are discussing about AC machines, especially transformers, we use the iron core to transfer the magnetic flux from primary to secondary. So whenever we are giving primary supply, the flux will be generated that will be linked through the magnetic core and the secondary EMF will be generated. Here we have to understand that iron core is the medium for transmitting magnetic flux. So that iron core or whatever the material we used depends on that material, the permeability and the magnetic flux density is depends. So whenever we are using that alternating flux to transmit through the iron core, we have to consider mainly two losses. One is hysteresis loss, another one is the eddy current losses. We are discussing about transformer losses. One of the most important losses are iron losses or core losses. So those core losses are nothing but hysteresis losses and eddy current losses. Now we are going to discuss about those two losses in detail in this video. Let's go into it. So when the magnetic materials are subjected to alternating flux, there are two types of losses occur. One is hysteresis losses and another one is eddy current losses. Now let's discuss about hysteresis losses first. Hysteresis losses are mainly occur in the magnetic materials when an alternating flux is applied to the magnetic materials. To understand this hysteresis losses, we have to draw a hysteresis loop between magnetic force and magnetic flux density. So the magnetic force, or we can take it as a MMF, applied to the magnetic materials, then the magnetic flux density will be generated. The flux will be generated. When you are giving a positive magnetic force, then the magnetic flux will be generated positive. When reduces the magnetic force, then the flux density also reduces. It is directly proportional. Let's see how the magnetic hysteresis loop will be existed between these two. One is magnetic force, another one is magnetic flux density. Okay, hysteresis loop is plotted between magnetic flux density B and magnetic force H. Okay, let's see the hysteresis loop. I will draw here. Okay, I can take magnetic force on the x-axis, magnetic flux density V on the y-axis. This is flux density and this is magnetic force. So this is positive value, on this side is a negative value. Positive value here magnetic flux density and negative value here. Now if I apply magnetic force, if I apply magnetic force in positive direction, then the magnetic flux density in the magnetic materials will also increases. So it will start from point O. If I increase magnetic force on positive side, this magnetic flux density also increases and reaches to some point A. So after that point, even though if you are increasing that magnetic force, the magnetic flux density will not increases because it will reach the saturation point. After that point, the magnetic flux density will be constant at, that is saturation point. If I want to make that flux density 0, I have to reduce the magnetic force. If I reduce the magnetic flux, and then magnetic flux density is also reduced. If I reduce the magnetic force, then the curve traces in this way. It will trace the path AB. Even though if you are applying zero magnetic force, that magnetic flux density is not zero. The reason for it is that magnetic material have a tendency to store some magnetic flux. That magnitude OB is called as residual flux. Residual flux nothing but, even though if you are applying zero magnetic force, the magnetic material will have some magnetic flux density. It is not zero. To make that magnetic flux density zero, we have to apply that magnetic force in the reverse direction. That means we have to apply negative magnetic force to make that magnetic flux zero. So I can apply in the reverse direction, then this curve will traces from B to some point C on the x-axis. So that means the force, this CO is amount of force applied to make that magnetic flux zero. So that CO is called, OC magnitude is called coercive force. The force required to make that magnetic flux density to zero. So if I further increased, then it will reach us to point, further it increases, if it reaches to point D, then if I want to make 0, then it will reach us to point E. If I further increases, it will reach us point like this. Path will be D, E, F. That means if we apply positive magnetic force, the magnetic flux density increases. Even if I applied zero magnetic force, it will have some magnetic flux, that is called residual flux. To make that residual flux zero, I have to apply in the reverse direction. I have to use some force, that is called coercive force. Okay, let's discuss. So I written here, the starting at O, the magnetizing curve follows the curve OA. If the MMF is gradually reduced, the flux curve follows the line AB. That means if I reduce in this direction, the curve will follows AB. As the MMF is reversed, the flux falls into the point C and hence to D. And as the MMF is returned to 0, the flux traces the path DE, then the MMF is again increased, the curve EFD is followed. So this is called the hysteresis loop. This loop may be different for different materials. So the area of this loop indicates the hysteresis losses. If the area is very much larger, that means one cycle increasing reaches to saturation, again becomes to 0, again going to the same point. That is called one closed loop or one closed cycle. This area is the indication of hysteresis losses. Some magnetic materials may have very small area. That means those magnetic materials are having very less hysteresis coefficient. Those materials are very strong magnetic materials. For example, if I use silicon steel, the hysteresis coefficient is very less. If you draw this hysteresis loop for the silicon steel, that loop will be very thin. That area indicates the losses, hysteresis losses. So to choose the best magnetic material, if you draw the hysteresis loop between magnetic force and magnetic flux density, if the loop area is very less, then that magnetic material is very strong magnets. Okay, so if you use those magnetic materials, then the hysteresis losses will be very less. I already mentioned, whatever the loss is converted to heat energy, then the magnetic core will become heat. And the distance OB measured of the residual flux, it will be indicated as BR. If the residual flux is very much high, indicates that there is no air gaps in the magnetic material. If the air gaps are there, it can't store that magnetic flux as a residual. Resistance OC is known as a coercive force. HR is the value of the demagnetization MMF required to bring the residual flux to zero. I already said. So we have to some additional force to make that flux density to zero. That force is nothing but coercive force. If your ferromagnetic material is subjected to an alternating MMF, the first hysteresis loop traces of the do not necessarily fall upon the edges. Suppose if you have drawn one hysteresis loop one time, if you draw the same hysteresis loop for the same material, it may not be the same hysteresis loop. It may be different, but we have to take at the first time. Right? The actual shape and area of the loop depends on the internal structure and composition of ferromagnetizing substances. So here they mention, so this is A1, suppose A2 and area 3, then A1 is greater than, A2 greater than, A3, A3 is represented as best magnetic material. So narrow hysteresis loop implies the small amount of dissipating energy in the repeatedly reversing the magnetization. That means that magnetic material is suitable for the magnetic core. Now, this hysteresis losses can be calculated with the formula. So the work done is nothing but the area of the BH loop, that will be joules per meter cube for one cycle. The Siemens is a scientist developed an empirical equation or relationship to express these losses. So pH is the hysteresis loss in watt. So this is the hysteresis loss. Kh is the hysteresis coefficient and F is the frequency of magnetization and K is the Siemens coefficient. Sometimes in the numericals we will take it as a 1.6. The value of Siemens coefficient is approximately equal to 2. Approximately equal to 2. In the numerical problems we will take this value as a 1.6. The low coefficient is preferred in order to reduce the hysteresis losses. We already discussed. So this is the hysteresis coefficient given for different materials. For cast iron it is 28.63 and steel iron it will be 10.05 and this silicon steel, yes, this silicon steel has lowest coefficient, that is 1.91. That means this material is best suitable for magnetic core. Our next one is eddy current losses. Eddy current losses is also a core losses. When you are using that magnetic materials, that iron is sometimes it will act as a small conductor. If the flux is moving, alternating flux moving through the iron core, this conductor will cut that magnetic flux. A small amount of EMF is induced. Because of that small induced EMF, some circulating currents will be generated in the iron core. Those currents increase the temperature of the iron core. So we have to avoid those eddy currents. So those currents will generated in the iron core because of that alternating flux cuts by that small iron conductors. Okay, so the term eddy currents is applied to those currents which circulate within the mass conducting material when the lot is situated in the varying magnetic field. So when that varying magnetic field is situated or applied to that iron core, some small eddy currents will be generated. The conductor material may be considered as a consist of large number of closed conducting paths, each of which behaves as a short circuit. We can reduce those eddy currents by lamination. How can we reduce those eddy currents by using laminations? By doing the laminations, we can reduce the area of the magnetic core. So what will happen if you reduce the area? If I reduce the area for any conductor, I can increase the resistance by using formula R is equal to rho L by A. If I reduce the area, then the resistance of that material will be increased. If I increase the resistance, automatically the eddy currents will reduce. So in this fashion, I can reduce the eddy currents by increasing the resistance or reducing the area of the core. How can I reduce? By using small pieces or laminating the core. So how lamination will be like this? So you can see here. This is the laminated core, single lamination. We have to make small pieces or laminations, and after that we can staggering or using bolts to combine those. With this I can reduce the area so that I can increase the resistance. Then I can reduce that eddy currents. So first, if I use the solid core, the currents will be in this fashion. So much currents will be flown. If I thick laminations, the currents will be reduced in this way. If I use these thin laminations, the small amounts of currents will be there. The effect will be reduced. So decreasing eddy currents. So the formula for these eddy currents will be follow this equation: F square B max whole square into T square, where T is the thickness, where T is the thickness of the material. So it is directly proportional to the square. It is directly proportional to the square of the frequency and square of the maximum magnetic flux density. Right? This is the eddy current losses. When you are comparing these eddy current losses and hysteresis losses, by definition, the losses occur because of relative motion between the core and magnetic flux. So when the relative motion is there, then the EMF induced. The losses which occur because of reversal of the magnetism is known as the hysteresis. Whenever you are giving alternating supply, sometimes it will goes to maximum value, sometimes it will go to zero, sometimes it will be negative cycle. When you are calculating the efficiency, first of all, we have to know the losses. This is the detailed information about the losses in the magnetic materials. I hope you all learned something about losses in the magnetic materials. Thank you.